In number 1, we are just looking for y prime. So that means we need to take the derivative of this function and then get y prime by itself. This is implicit differentiation. The derivative of x with respect to x is 1. The derivative of y with respect to x is 1 y prime, 6y y prime, and for 4y cubed we get 12y squared y prime. Let's factor out a y prime on the right. Factoring that out, we get 1 plus 6y plus 12y squared. Divide by all of this, and that gives our answer. Y prime is 1 over 1 plus 6y plus 12y squared. Moving down to number 2, we're looking for dy dx, which is exactly the same as y prime. We're going to solve this problem the exact same way. We take the derivative implicitly of this entire equation. The derivative with respect to x of x squared is 2x. The derivative of y squared is 2y times y prime. And on the right here, you see we have a product rule, 2x times y. So we'll treat that like a product rule. The derivative of 2x is 2 times the second function y, plus the derivative of y, which is y prime, times the function 2x. Now we need to treat y prime like a variable to get it alone. It doesn't matter which side you bring your y primes to. I'm going to bring them to the left side. I've got 2y y prime minus 2x y prime equals 2y minus 2x. Factor out a y prime on the left. Y prime times 2y minus 2x equals 2y minus 2x. When we divide by 2y minus 2x, we see that y prime is 1. Let's move down to number 3. This problem appears very difficult because the right-hand side looks like it's a quotient rule. I prefer to avoid quotient rules as they take more time than the other rules, and I'm going to multiply both sides of the equation by xy, thereby eliminating the quotient rule. So, multiplying by xy on the left gives xy squared, and on the right, simply y plus x. Now, instead of a quotient, we have a product. Alright, the derivative of this with respect to x. On the left side, our product rule, the derivative of x is 1 times y squared, plus the derivative of y squared, which is going to be 2y y prime times x. This is just a product rule. Equals the derivative of y is y prime, plus the derivative of x with respect to x is 1. We need to get y prime by itself. It's going to be y minus 1 equals y prime minus 2y y prime. Solving for y prime now, we have y minus 1 equals y prime times 1 minus 2y. And that means y prime is y minus 1 over 1 minus 2y. As you can see with all of these implicit problems, as they get more complicated, factoring becomes a step that appears often. Don't forget your algebra. Moving on to number 4. Interesting problems at last, related rates. How fast is the area of a square increasing when the side is 3 meters in length and growing at a rate of 0.8 meters per minute. All right, step one is always figuring out what formula we're going to use. There's a vast array of math formulas that we know. In this problem, we focus on the area of a square. Well, I know the area of a square is the length of one side squared, so I'm just going to use area equals x squared. All right, this whole problem has to do with a square when its side length is 3 meters and it's growing at a rate of 0.8 meters per minute. I use x prime for the rate of change of the side length x, and those are the only variables we have. We're searching for how fast the area is changing. That means we're looking for a prime. Our equation here does not have a prime in it, but if I take the derivative with respect to time, because everything's changing over time, we get the derivative of a with respect to t is a prime. The derivative of x squared with respect to t is 2x times x prime. Now we plug everything in. A prime is equal to 2 times 3 times 0.8. And that gives us 4.8 meters squared per minute. In number 5, we're dealing with a sphere whose radius is increasing at a constant rate of 0.05 centimeters per second. And at the time when the radius of the sphere is 10 centimeters, what is the rate of increase of the volume? So we need some formula for the volume of a sphere. Oh, they gave it to us. The AP test will also give you formulas for volumes of spheres. So if the volume is 4/3 pi r cubed, and we want to see this as it changes over time, we take the derivative with respect to time. The derivative of v with respect to t is v prime. And the derivative of everything on the right there is 4 pi r squared times r prime. Looking at the problem, we have a little bit of information here. R is equal to 10, and r prime is equal to 0.05. Plugging this into the problem, v prime equals 4 times pi times 10 squared times 0.05. And that gives us v prime is 20 pi. That's a rate of change of volume, and this problem is in cubic centimeters per second. Moving on to number 6. A boat is being pulled toward a pier by means of a taut cable. If the boat is 20 feet below the level of the pier and the cable is pulled at a rate of 36 feet per minute, how fast is the boat moving when it is 48 feet from the base of the pier? Let's draw a picture of this. We have water and a pier with a boat out here. Okay, the rope tied from the pier to the boat forms a right triangle, and we can tell exactly what kind of problem this is going to be. I'm going to pull up a new sheet to... Moving on to number 7. In number 7, a clown's blowing up a bubble, which is in the shape of a sphere. If it's inflated at a rate of 6 cubic feet per minute. Okay, so 6 cubic feet per minute is a rate of change of volume. So I'm going to go ahead and write that down. V prime is 6. What is the volume of the balloon when the radius is increasing at a rate of 3 inches per minute? Now, this is a bit concerning. We have cubic feet and inches. It is not okay to work the problem half in feet and half in inches. We need to pick one. Given that all the answers are in cubic feet, I choose to do feet. So r prime, 3 inches out of 12 inches for a foot means that 3 inches is 0.25 feet per minute. We go back to our volume of a sphere. 4/3 pi r cubed. And we take the derivative of that with respect to time. Everything is changing as time changes. And we get v prime equals 4 pi r squared times r prime. Plugging in our numbers, we get 6 is equal to 4 pi r squared times 0.25. After a little bit of algebra, we see that r is equal to the square root of 6 over pi. The problem is not looking for r, though. It's looking for what is the volume of the balloon at this point in time. Well, once we have this, we take that and we plug it back into our original volume formula. And after some simplifying, we get d. Moving on to number 8. We have two vehicles approaching an intersection. A car from the east going 12 meters per second, and a van from the south going 16 meters per second. And we're looking for how fast the distance between them is changing at a particular point in time when the car is 30 meters east and the van is 40 meters south. This is a clear Pythagorean theorem problem. A squared plus b squared equals c squared is the formula we'll use. And we'll let a be the small side 30, b 40, and c would be 50. A prime, this rate at which this side is changing, is negative 12. It's shrinking at a rate of 12 meters per second. B prime is the rate at which this side is shrinking, and that's shrinking at a rate of negative 16. Well, it's changing at a rate of negative 16 meters per second. And we're searching for C prime. We take our derivative with respect to time, because everything is with respect to time here. And 2a times a prime plus 2b times b prime equals 2c times c prime. We plug a prime, b prime, and c all into the equation. We solve for c prime, and c prime is 20 meters per second. Okay, so there's our right triangle. The boat is 20 feet below the pier, and we want to know when it's 48 feet away, how fast is the boat moving toward the pier if the cable is being pulled in at a rate of 36 feet per minute. A little old Pythagorean theorem reveals that the length of the hypotenuse right now is 52 feet. Let's go ahead and write our equation. A squared plus B squared equals C squared. We're going to take the derivative of this with respect to time, because over time the lengths of these sides of this triangle may be changing. So the derivative is 2a times a prime plus 2b times b prime equals 2c times c prime. There are a lot of variables here, so I'd better label them. I'm going to make my a 48. My a prime then is the speed at which this side is changing, and that is exactly what I'm looking for. My b is the 20. B prime, that's how fast is the height of this pier changing. Well, the pier does not change height, so b prime is 0. C is the length of the hypotenuse, which right now is 52 feet, and c prime, the length of which it's changing, it's getting pulled in at negative 36 feet per minute. It's getting smaller by 36 feet per minute. Plugging these into our equation, 2 times 48 times a prime plus 2 times 20 times 0 equals 2 times 52 times negative 36. A little algebra reveals that a prime is negative 39. To label it, that would be in feet per minute. We expect it to be negative because the boat is getting closer to the dock. The length of this side is shrinking. Number 9. This problem is one of the most difficult ones in the review, even though it looks very short. At what points on the ellipse is the slope of the tangent line equal to 4? So to start out, I'm going to multiply this equation by 144 just to eliminate some fractions and scare people a little bit less. Multiplying by 144 gives us 16x squared plus 9y squared equals 144. What we're most concerned with is the slope. When is the slope equal to 4? Well, to find the slope, we just take the derivative. We're looking for the slope, so our derivative is with respect to x, d dx, the derivative of the function with respect to x, and the derivative is going to be 32x plus 18y, y prime, equals 0. Solving for y prime, we get y prime is equal to negative 32x over 18y. Which simplifies into negative 16x over 9y. So we need to know what points exist on this curve wherein the slope is equal to 4. We now have two different equations and two unknowns x and y. Use any method to solve this you'd like. I would prefer substitution. I'd change this second equation into y equals negative 4 ninths x, or negative 4x over 9. Then we'd take that and substitute into your top equation. I'll leave the algebra to you. Moving to the last problem. sand is falling off, typo, missing a word, of a conveyor belt, or off of a conveyor onto a conical pile at a rate of 20 cubic feet per minute. The diameter of the base of the cone is 4 times the altitude. At what rate is the height of the pile changing when it is 8 feet high? Let's draw a picture of this one. So here's our pile of sand. And we have a conveyor belt that's dropping the sand onto the pile. The diameter of the base, the diameter of the pile, is 4 times the altitude. That might be relevant. So my D equals 4 times height. One thing that is glaringly missing from this problem is the formula for the volume of a cone. On your test and on the AP test, that would be given to you. It's 1/3 pi r squared h. Because you know it's going to be a related rates problem, a lot of people are tempted to dive straight into the derivative. You know you have to take a derivative here. The problem is if we take this derivative right now, we have a product rule over here, which is fine. We can do related rates with product rules. But if we can recognize a relationship in these types of problems between the radius and the height, we can make this problem much, much easier. So let's focus on the formula they gave us. That the diameter is 4 times the height. Well, diameter is not part of our equation, so let's change that to the 2 times the radius is 4 times the height, which means the radius is equal to 2 times the height. This would also mean the height is 1/2 the radius, but since this problem is all about height, I'm going to use this equation so I can substitute 2h in for my radius and write my volume equation all in terms of height. In other words, the volume is going to equal 1/3 times pi times 2h squared times h. Then we algebra. 1/3 times pi times 4h squared h, which is 4/3 pi times h cubed. Taking the derivative, v prime is equal to 4 pi h squared times h prime. I realize now I didn't write down any of my variables. The problem only gave me 2 things. It told me that v prime was 20, and it told me that we wanted to know h prime when h is equal to 8. Thankfully, this is enough information to solve this thing. So 20 equals 4 pi times 64 times h prime. And a little bit of algebra says h prime is going to equal 20 over 4 times pi times 64. And that simplifies into 5 over 64 pi. This is h prime, the rate of change of the height. And this problem, everything is in feet per minute. So that's going to be 5 over 64 pi feet per minute. If you have any questions, feel free to email me, Skype me, or ask me in class. See you there.